Okay, so this is your walkthrough of your A2 Polymers questions homework. As usual, look for the right answers, and if not correct, please correct them carefully. So first of all, we've got two polymers here, and we have to deduce the monomers. Polymer L, if you look at the main carbon chain, you can see that this must be an addition polymer. There are no oxygen atoms or nitrogen atoms in the main backbone of the polymer, and so this tells you it must be an addition polymer coming from an alkene. So all we do is we take away the bond between the main repeating units. We find two carbon atom repeating units, and we replace the double bond between the two carbon atoms in the main backbone. This part, the side chains of this polymer, don't change. So we can see that this is our monomer here. It's actually phenylethene or styrene. So this polymer is polystyrene. Polymer M, we can see that there's a very different backbone. If we follow it through, we've got carbons, oxygens, and also benzene rings within that. So this must be a condensation polymer. So what we're looking for is either an ester or an amide link. And I can see here that we've got a carbonyl next to an oxygen, carbonyls next to oxygens, so this must be a polyester. So we're going to break the ester links. So if we do that and we break the ester links between our monomers, hopefully we can see what our monomers might be. So first of all here, this has got a carbonyl at either end, so this must be a dicarboxylic acid with a benzene ring in the middle. And here we've got an oxygen at the end, so this must have been a diol. These are going to be OH groups. So these are our two monomers. So part B, this time we're given the monomer, and we can see it's a hydroxycarboxylic acid, so it's a monomer that can be used for a polyester, and we need to suggest a structure for our polymer showing 3 repeat units, so 3 lots of this molecule, 1, 2, 3, remembering that the whole of the OH comes off the carboxylic acid, leaving behind just the carbonyl, the C double bond O, and just the hydrogen comes off the OH, joining on to the other end here. Part C asks us about the type of polymerisation, and because we can clearly see we've got ester links, that's a condensation polymer, and the key feature of that is that water is produced as well as the polymer in its formation. A major use for polyesters, we should have 3 simple options here: clothing, fibres, plastic bottles. Question 2 is quite similar. Again, we're going to have some polymers. We've got to spot the repeating units, and with a carbon chain, carbon, 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 we know it's got to be an addition polymer, and so we need to find one repeating unit that has 2 carbon atoms only in it. And then because we've got oxygens in our chain and also benzene ring, we know here we've got a condensation polymer, and so we're going to break the ester links to find our repeating unit. Now you'll notice that where I've broken the ester links here and here, we've got one option for a repeating unit there. But equally, you could argue that this is a repeating unit too, because if we continue from here and stop here, the pattern starts again here and continues. So the other option here is that, of course, this is also a repeating unit, starting with the O and finishing at this carbon here. Polymer D is formed by a condensation reaction, and next we have to deduce the 2 monomers. So we're going to break the ester links between the carbonyls and the oxygens. Hopefully we can then see quite clearly that we've got a dicarboxylic acid. The presence of these 2 carbonyls indicates the presence of 2 carboxylic acid groups. and then this section here is going to become a diol, ethane 1,2 diol, and it repeats again. Part B asks why polymer D is more susceptible to hydrolysis than C. Now remember, hydrolysis is a reaction with water or hydroxide ions, and polymer D has got polar carbon-oxygen bonds within the main chain of the polymer. And because they're polar, they're more susceptible to attack by water or hydroxide ions. Water and hydroxide ions have a lone pair, so they can attack the delta positive carbon in those polar carbon-oxygen bonds and break that bond. Now, of course, in an addition polymer, we don't have any polar bonds in the main carbon chain, and so hydrolysis is unlikely to occur. So there's the answer. Question 3 is about the polymer nylon, and it asks for a similarity to a protein, and the similarity is the presence of the very distinctive amide link. So we kind of compare this to the ester link in a polyester. This is an amide link, a carbonyl bond next to a nitrogen. The difference of nylon to a protein, of course, is that a protein is natural and nylon is synthetic or man-made. The monomers that make this come from breaking, this time, the amide links between the nitrogen and the carbonyl, and then what we do is we replace the hydrogen on each of the amine groups and we place the OH on each of the carbonyls to give us our monomers. Notice that this question asks for displayed formulas, so I've been a little bit lazy with the way I've drawn those monomers out, but you get the idea. Remember, of course, that even the OH bonds in the carboxylic acid groups should be drawn out if it asks for a displayed formula. And wherever we have peptide or amide groups within a polymer or a polypeptide, we can have hydrogen bonding. The hydrogen on the amine part of the amine is obviously attached to a nitrogen, which is highly electronegative. So this hydrogen here is attracted to a lone pair on a nitrogen of a neighbouring amide or peptide group. So you must show the dipoles, you must show lone pair on the nitrogen, and then a dotted or dashed line between the lone pair and a delta positive hydrogen is the hydrogen bond, and that's where the 3 marks come from here. For question 4, let's first think about what type of polymer we've got here. I know the question is not really asking for it yet, but I want to emphasise again, the main chain is only carbon, so this is an addition polymer. Now we circle the repeat unit by taking 2 carbons. Any 2 would do, even these 2 would do. And we circle the repeat unit. I've just chosen this one as my 2 carbon atoms. Now for the empirical formula, for each repeat unit, count the number of carbons and hydrogens. 4 carbons, and then 2 plus 3 plus 3 is 8 hydrogens. So that's 4 to 8, which is, in simple terms, 1 to 2. So the empirical formula is CH2. To draw the monomer for this, as we did earlier, we break the bonds between repeating units and we replace the double bond between the 2 carbons. So we've actually got, in the end, methyl propene. Don't need to name it. If you just simply draw out the same 4 groups that are on those 4 positions in the monomer into the polymer. So now we're asked about the polymerization of amino acids to make proteins, and by doing this they form the amide or the peptide link, and that's the way we draw the amide or the peptide functional group. That's of course formed by a condensation reaction. We're seeing some repetition now in the same sorts of questions. For a dipeptide made from glycine, we need to take a hydrogen from one end on the amine part of the amino acid, and we need to take the whole of the OH from the carboxylic acid group on another amino acid. So this dipeptide consists of two molecules of glycine, and in the middle here, the amide link, is where the OH has been removed from the carboxylic acid, this amino acid, and the hydrogen has been removed from the amine of this amino acid. And notice that the two ends of this dipeptide are complete: NH2 amine and COOH, carboxylic acid. The skeletal formula takes a bit more practice perhaps. Remember, the carbons and any hydrogens attached to those carbons are not shown in a skeletal formula. Other hydrogens are shown. The ones joined to oxygens or nitrogens are shown. A percentage yield is quite a common question in F324, where we've got large molecules. We might need to think carefully about how many moles of product we're expecting and how many moles of product we actually get. Now often the molar ratio of reactant to product is 1:1, but in this case, because we're making a dipeptide, if we start by working out the moles of glycine, so that's the mass divided by the MR, which gives us 0.0187 moles, the amount of moles of the product we expect to get is half that. Why? Because we'd need 2 moles of glycine to give us 1 mole of dipeptide. It's a 2:1 ratio. So if the moles of glycine is this, the moles of the dipeptide is this, half that number. Now next we're going to calculate the number of moles of the product. So there's the mass of product and there's the MR of the product. Mass over MR gives us the moles. So this is what we expected to get, this is what we did get, and so the percentage yield is 89.3%. With HCl, an amino acid will have its amine group react because an acid reacts with a base. So the base will accept a proton, NH2 becomes NH3+, and you can draw that with or without the chloride ion, which would be attracted to the NH3+ group. Okay, so another question about nylon, or a type of nylon, and this time we're not given the displayed formula of the polymer, so it's a little bit more difficult to see the links, but hopefully you can recognise CONH2 as an amide link between monomers. And so if we break those links between the carbons and the nitrogens, we should be able to see where our monomers are. Now it says identify the monomers, it doesn't say name them, although I have given you the names here, so the diagrams would be sufficient. On this side of the monomer we want to replace the OH, and on this side the same. We've got the carbonyl, the C double bond O, we want the OH, so that becomes the complete acid group. On this monomer here we're replacing the hydrogen to make the amine parts intact, so we get a diamine with 6 CH2s in the middle. Once again, it's condensation polymerization, because as well as producing our polymer, we produce water when the hydrogen and the OH come together. Because proteins and polypeptides have both got amide links joining together the amino acids, they're similar to nylon, because nylon also forms an amide link where an amine group reacts with a carboxylic acid group. So a structural similarity between nylon and a protein or polypeptide would either be the presence of the amide link or possibly the fact that hydrogen bonds can form between molecules, and you might want to draw a diagram either just to show the hydrogen bonding between the molecules or simply to demonstrate that you understand that this is the peptide link that is the similarity between them, or the amide link. A chemical similarity, both of them can be hydrolyzed, so under acid aqueous reflux conditions or alkaline aqueous reflux conditions, that amide will be broken down and hydrolyzed. Differences between polypeptides or proteins and nylon. Main one is going to be that protein is a natural substance and nylon is synthetic or man-made. You may also want to discuss the monomers that could be used to make them, but I think it's much more simple to talk about natural and man-made. Last of all, for question 6, we need to mention 2 other alkenes apart from propene that you might find in the top 20 feedstocks. Now, a feedstock is a chemical compound that can be used in industry to make a new compound. So a chemical company might buy something like propene in order to change it into something else, for example, polypropene. So in that case, propene is the feedstock. It's the product that has to be bought in by the company. 2 other top 20 feedstocks would be any other alkenes like ethene or maybe chloroethene. And why? Well, because again, they can be polymerized. We can get polyethene or polychloroethene, which would actually be PVC, and really any other alkene you can think of, which would also be used to make a polymer. Part B is from an old question, and you don't need to do that, so apologies if you've spent a lot of time thinking about that one, but that's the end of that piece of work.